right, class, so let's talk about the steps to finding complex zeros of a function. So the first thing we want to know, and it's a theorem we learned in the last section, is that the degree of the polynomial is the number of zeros. Our step one is going to be to find the rational zeros. We're going to factor the polynomial for the remaining quadratic, and we can use the quadratic formula to find our complex zeros. So let's work through a couple of examples. This first example, x to the fourth plus 5x squared plus 4 is a little bit different. It's a little bit different because we're going to have to use substitution. The reason I know this is if I was to graph this polynomial, it looks something kind of like this. It never intersects our x-axis, so it never has any zeros. So let me show you how we're going to use substitution. Substitution is something we covered earlier on in this course. If you want a link to the video, shoot me an email and I will give it to you. So if I have, let's use orange, f of x equals x to the fourth plus 5x squared plus 4, we're going to use substitution to solve this. We're going to let u equal x squared. So now I have f of u equals x equals u squared plus 5u plus 4. Now I can use the quadratic formula to solve for my u's. We label our ABCs. A is 1, B is 5, C is 4. So u equals negative b plus or minus the square root of b squared minus 4ac all over 2a. U equals negative 5 plus or minus 25 minus 16 over, because 4 times 1 times 4 is 16, over 2 times 1, which is 2. U equals negative 5 plus or minus the square root of 9 over 2. So u equals negative 5 plus or minus 3 over 2. So u is negative 5 plus 3 over 2, or u is negative 5 minus 3 over 2. So I get that u is negative 2 over 2, which is negative 1, or u is negative 8 over 2, which is negative 4. And you might say, hey, Miss Miller, this doesn't look like complex zeros. And to that I would say, wait, because we didn't solve for x, we solved for u, and u equals x squared. So if I have to set each of my u values equal to x squared, I have negative 1 equals x squared, and negative 4 equals x squared. I'm going to take the square root of both sides to solve these. I get that the square root of negative 1 equals x, so x is plus or minus I. I get that x equals plus or minus the square root of negative 4, which is 2i. So my zeros are x equals negative I, negative 2i, and positive 2i. See, I've got my complex conjugates already together. So if I wanted to write f of x fully factored, f of x would equal x plus I, x minus I, x plus 2i, x minus 2i. And if I was to FOIL this bad boy out, I'd get back to my original degree 4 polynomial. So for problem 2, f of x equals x cubed minus x squared plus 3x plus 37x minus 50, I'm going to go ahead and find all of our zeros for this polynomial. So what I'm going to do first is I want to find my mind my p's and q's, right? I want to find my list of all possible rational zeros. And that's minus 50. So I have p could be plus or minus 1, plus or minus 2, all the factors of 50, right? Plus or minus 5, plus or minus 10, plus or minus 25, and plus or minus 50. Luckily for me, my possible q's are just 1. So my possible rational zeros are all the factors of 50, which is plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10, plus or minus 25, and plus or minus 50. So I'm going to use the remainder theorem to find my rational zeros. And the remainder theorem says if I have f of p over q equals 0, then x minus p over q is a factor. So I'm going to take f of negative 1. That gives me negative 1 cubed minus 8 times negative 1 squared plus 37 times negative 1 minus 50. That gives me negative 1 minus 8 minus 37 minus 50, which gives us a negative 96. So f of negative 1 is not a rational zero. I'm going to take f of positive 1. That gives me 1 cubed minus 8 times 1 squared minus 37 times plus 37 times 1 minus 50. That gives me 1 minus 8 plus 37 minus 50, which is indeed a negative 20, and so 1 is also not a rational zero. So let's check f of 2. F of 2 equals 2 cubed minus 8 times 2 squared plus 37 times 2 minus 50. So f of 2 equals 8 minus 32 plus 37 times 2, which is 74 minus 50, and that's going to give me 0. So I know that x minus 2 is a factor. So what do I find out? How do I find out what my remaining degree 2 polynomial is when I pull out an x minus 2 factor? And that's going to be to use synthetic division. So I just found that f of 2 equals 0. So x minus 2 is a factor of f of x. I need to use synthetic division to determine my remaining degree 2 polynomial. So I have 2, and then I put in my coefficients, so x cubed is 1, minus 8x squared plus 37x minus 50. Pull this 1 down. 2 times 1 is 2. Negative 8 times 2, negative 8 and 2 is negative 6. 2 times negative 6 is negative 12. 37 and negative 12 is 25. 2 times 25 is 50, so I have a remainder of 0. So this leaves me with x squared, because my degree goes down by 1, minus 6x plus 25. So now I have f of x equals x minus 2 times x squared minus 6x plus 25. I now have to go ahead and factor the remaining quadratic. So I say, okay, what are the factors of AC that add up to b? Well, darn it if that doesn't work. There are no factors of 25 that add up to negative 6. So I'm going to have to use the quadratic formula. A great place to start is with our A, B, C's. So I have x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So x equals a negative 6 plus or minus the square root of negative 6 squared minus 4 times 1 times 25 all over 2 times 1, which is 2. So x equals 6 plus or minus the square root of 36 minus 100, which is a negative 64 all over 2. So x equals 6 plus or minus 8i divided by 2. Oh no, I've reached my limit. So x equals 6 plus or minus 8i over 2. So I find that x equals 3 plus or minus 4i. So my x's factor into a 3 plus 4i and a 3 minus 4i. Those are my two possible x's. So I have f of x equals x minus 2. This is its fully factored form. F of x equals x minus 2 times x minus 3 plus 4i times x minus 3 minus 4i. So f of x has the zeros 2, 3 plus 4i, and 3 minus 4i. Those are my zeros. Notice I have two complex conjugates together. The next question is to find a polynomial whose zeros are given. So if I want to find a degree 3 polynomial whose zeros are 3 and 4 minus I know that I also need to have a zero of 4 plus I. So I'm going to go ahead and write this out because I want to find a polynomial with this layout. So I have f of x equals a, where a's are constant of shrinking or vertical stretching or shrinking. That's okay. I've got x minus 3, x minus 4 minus I, and x minus 4 plus I. I'm going to simplify. F of x equals x minus 3 times x minus 4 plus I times x minus 4 minus I. And I noticed that these, if I rewrote it like this is the product of a sum and a difference. For example, if I have x plus 2 times x minus 2, that becomes x squared minus 2 squared. So I'm going to go ahead and write this as f of x equals x minus 3 times x minus 4 squared minus I squared. Remember that I squared, I've got all these little side notes, I squared is negative 1. So I have f of x equals x minus 3 times x minus 4 squared, which is x squared minus 8x plus 16 minus a negative 1. So I have f of x equals x minus 3 times x squared minus 8x plus 17, and then I go ahead and distribute. So I get f of x equals x cubed, x times x squared is x cubed, minus 8x squared plus 17x minus 3x squared plus 24x minus 51. And if I combine all my like terms, I get f of x equals x cubed minus 11x squared plus 31x minus 51. I'm going to highlight some stuff real quick. So like this step right here was the key step where I wrote it as the product of a sum and a difference. If I tried to FOIL it out otherwise, it wouldn't work as well. So just a friendly reminder that that's our key step. Let's take a look at this next example. We'll do it in green. I've got 4 zeros, I, 7, and negative 7. Well, if I have I know I have to have negative I as one of my zeros. So I'm going to write this as f of x, where there's some a constant in front of it. Guys, remember you could have some a in front of it because there isn't just one polynomial with these zeros. There are infinitely many depending upon the a. So f of x is a times x minus 7, x plus 7, x minus I, x plus I. So f of x equals, I'm going to go ahead and FOIL out these the product of a sum and a difference. So if I have x minus 7 times x plus 7, that gives me x squared minus 49. And if I have x minus I times x plus I, that gives me x squared minus an I squared. Well, that's really x squared plus 1. So f of x is a, x squared minus 49 times x squared plus 1. So I FOIL that out. I get f of x is a, which is some leading constant, x to the 4th minus 49 x squared plus x squared minus 49. I didn't FOIL that properly. I did that out of order. Why don't we try that again? Okay, so I've got x squared times x squared, which is x to the fourth, x squared times 1, which is x squared, negative 49 times x squared, which is negative 49x squared, and negative 49 times 1, which is negative 49. So final answer, f of x equals a, x to the fourth minus 48x squared minus 49. If you have any more questions or would like any more examples, feel free to shoot me an email, and I can definitely make some more videos over complex polynomials and complex zeros.